Hello, Professor. I'm Karthik Abram Bhamadpati here. I'm here to present our project on the study of burden of chronic diseases over activity participation. My team consists of four members: myself, Fanindra Reddy Maduru, Chinta Sridhar, and Rohit Reddy Mekla. Coming to the key driving force of our study, in 2012, a report from Global Burden of Diseases demonstrated that the disability of an individual increases as his or her age increases. And it is also proven that in US, the most common reasons for cause of disability are musculoskeletal, cardiovascular, diabetes, and cancer conditions. Also, it is estimated that 50% of adults in US will visit doctors to take care of these four disease conditions. And there are some studies that prove for persons having these four diseases will result in activity limitation, participation limitation in several activities such as walking, standing, bending, and doing shopping, social activities, etc. Now, our primary goal of the study is to assess the insights of data by finding the impact of these four health conditions on the activity limitation and participation limitation of an individual. Now, from where the data has come, the data for analysis was taken from 2012 National Health Interview Survey (NHIS), and it is an household survey in the US conducted by National Center for Health Statistics. And this data obtained from NHS is the principal source of health information of US population. The data considered in this project is of 2012 and consists of around more than 42,000 observations with an overall response rate of 77.6%. As mentioned earlier in our objective, our analysis focused on musculoskeletal and non-musculoskeletal health conditions, on activity and participation limitation of individuals. The survey has focused on various questions related to health conditions. For example, we can see the questionnaire in the screenshot. And the questionnaire has also questions pertaining to activity limitation, whether it depends on the difficulty of an individual to walk a quarter mile, or whether the individual can climb steps, etc. And the questionnaire has also questions pertaining to participation limitation, whether an individual can go to events without special equipment, or whether the individual can indulge in any enough social activities. And also the questions are linked for both health conditions and activity participation. The data which we are considering for the analysis have around 34,000 observations with 813 attributes. These 813 attributes are the different questions posed for the individuals in the questionnaire, and the average age of the individuals in the data is around 48.52 years, ranging from 18 to 85 years. And coming to the data manipulation, we have manipulated the variables those fall into similar health conditions into a single attribute. Let us suppose, for example, we have different daily activities such as standing, walking, sitting, climbing, etc. And the responses to these activities are grouped into a single attribute known as act limit. We'll see the description in the next slide in this SAS code. Whenever the individual have difficulties in walking, climbing, standing, sitting, then we are assigning the act limit response as 1. For variable reduction, we have considered those variables having the missing values more than 10,000. We are excluding those variables, and this assumption has reduced the variables from 813 to 216.
Hello Professor, this is Sridhar Chinta here, and I'll be walking you through the rest of the analysis. In this slide, we are showing you how the variables are selected. We are using Weka for this. In order to select the attributes which are most helpful for the analysis, attributes are ranked by their corresponding information gain percentage. So in Weka, we go to select attributes tab, and we choose the attribute evaluator as information gain attribute eval, and the method is ranker. So once we run this, we can see all the attributes ranked by the information gain percentages. After selecting the most important attributes for our analysis, we are further excluding few variables such as activity limitation, participation limitation, cardiovascular prevalence attribute, diabetes prevalence attribute, cancer prevalence attribute, since the influence of these attributes has already been accounted in the grouped variables, that is CDC disease and activity participation limitation attribute. In the variable selection process, we have also taken into account the advice of domain experts and further reduced the number of dimensions and attributes. The final count of the attributes has come down to 33. These are the final list of selected attributes. We also calculate the baseline accuracy of the model. We have used J48 tree algorithm, and the confidence factor is kept at 0.05. Since the most frequent outcome of a target variable is no, the baseline accuracy has come down to 64.84%. After building the final dataset and calculating the baseline accuracy, we are going to build our model in SAS Enterprise Miner. I've opened the SAS Enterprise Miner, and as you can see, all the nodes are already in place. So I'm just going to walk you through the process. The first node, the file import, is used to import our final dataset into SAS. As you can see, I'm using the location where the final dataset is to load my file. I'm in the Stat Explorer data node to study about the data. Let us see the results of the Stat Explorer. This is the results window of the Stat Explorer node. As you can see, this is the log worth value of all the attributes listed down here, and if you go to the output window, we can see the class variable summary statistics and the interval variable summary statistics. The interval variable summary statistics will give you the minimum, median, and the maximum values of the attributes. Also, the class variable summary statistics will give us the mode and the mode percentages of all the class variables. Let us close this results window. The data partition node is used to allocate data between training, validation, and test datasets. Here we can see 40% of the data is allocated for training, 30% for validation, and 30% for test datasets. I'm using the replacement node to replace the missing values for the attributes. So I'm selecting the replacement editor for class variables from here. This is a replacement editor window. SAS can only interpret a blank or a period as a missing value. For this particular attribute, there is a question mark which is not interpreted by SAS as a missing value. Hence, I am going to hardcode it as a missing value. There is another variable where it has missing values, and I'm going to do the same for that. Click OK. I'm using the control point to distribute the input data between two different models, that is decision tree and the interactive decision tree. First, I'm going to build a decision tree. Let us set the properties for the decision tree. The maximum depth is set as 10. The leaf size is set as 5. The number of surrogate rules is set as 5. Let us run the decision tree now. The decision tree has run, and let us check the results. This is the result window of the decision tree. If we go to the tree window, we can see the tree visualized. As you can see, the first split is made on FL push, which is nothing but the difficulty to push large objects, and the second split on the right side is made on difficulty to carry objects more than 10 pounds, and the subsequent splits are based on musculoskeletal prevalence, and so on and so forth. And on the left side, the second split is made on joints pain existence or not, and the subsequent splits are made on muscular skeletal prevalence and CDC disease prevalence. We'll analyze the decision tree in further slides. Now I'm going to build the interactive decision tree. So I'm selecting interactive from the property window. This is a root node of the decision tree. Select the node and we'll select action and split node. The first attribute is having the highest log worth, and we'll select this attribute to split the node. Click OK. As you can see, now the root node is split into two for the attribute FL push. We'll select the lower left attribute and perform the same action again, and select the topmost log worth attribute. Click on OK. We'll perform the similar steps for the right node, lower right node. As you can see, the nodes are split. Now there are 4 leaf nodes and 7 nodes in total. Now let me train the lower right node. Right click on it and click on train node. As you can see, the decision tree has built till there is a stopping criteria met. Let us leave this tree as such. This is an unpruned tree. Let me close the interactive decision tree window. Now I'm going to compare the two models. For that I'm using the control point 2, where the results from the two models are fed into the model comparison node. I'm going to run the model comparison node. The model comparison node has run. Let us check the results. This is the results window of the node model comparison node. As we can see, the decision tree has come out to be on top with the with the least misclassification rate of 0.16, and we'll go ahead and analyze the decision tree now. Let us close the model comparison results window. Let us examine the tree now again. Let us close the tree window to visualize the tree. So if we look at the node 13, we can say that. So if we look at the node 13, we can infer that if a patient has responded saying that it is difficult to push heavy objects and it is not difficult to carry 10 pounds of object and has musculoskeletal prevalence, then the patient is said to have activity participation limitation. And if we look at the another node, node 29, we can say that if a patient has musculoskeletal prevalence and CDC disease prevalence and has no joint pains and he does not feel difficult to push large objects, then their activity participation limitation is further dependent on other health conditions such as urinary problems. If they do not have any urinary problems, then the patient does not have any activity participation limitation 65% of the time. And for the last inference, let us look at the node 18. So in this inference, we can conclude that if a patient has no musculoskeletal prevalence and no CDC disease and has no joint pain symptoms, and he does not find any difficulty in pushing large objects, then that particular patient does not have any kind of activity participation limitation. So we can conclude that the activity participation limitation of a patient is dependent largely upon the difficulty level of performing physical activities like pushing large objects and whether they have any kind of musculoskeletal health conditions. The effect of CDC disease on ACT part limitation is further dependent on other health conditions. Therefore, the musculoskeletal prevalence and the physical activities are the most influencing factors in determining a patient's activity participation limitations. Thank you.